Hello, Math 201 students. We're looking at related rates, section 3.10. So related rates are going to be one of the ways that derivatives can apply to real-world situations. So it's like when you know how certain variables of a process or of a geometric structure relate to one another, as that structure or as that process changes, how do those variables change related to the changes of other variables? I'm being kind of vague there, but the problem of finding a rate of change from other known rates of change is called a related rates problem. So one example of that's given in the next page here. As you blow up a balloon. As you blow up a balloon, certainly there are many things that are changing about that balloon. The volume of air in the balloon is changing. The radius of if you consider it kind of like a sphere, the radius of that sphere is changing. The surface area of the outside of the balloon is changing. All those things are changing. So the one question would be, how are they changing in relation to one another? So if we can relate them with an equation, then we can do derivatives, and then that can relate their rates of change to one another as well. So let's take the equation of a sphere, like if you were blowing up a balloon that was modeled by a sphere. The volume of a sphere is this. It's 4/3 pi times the radius cubed. So if you were to take the derivative of both sides and we're talking about a rate of change. So we're taking the rate of change, the derivative of v with respect to what variable? If we're talking about a rate at which it changes, we're talking about how that thing changes over time. So we're taking the derivative of both sides, not with respect to v and not with respect to r, but with respect to a third variable, time. So the derivative of v with respect to time is dv dt. Or you could also use this notation, v prime of t. That's fine too. But dv dt equals, all right, what's the derivative of this with respect to time? Let me go back and do this one more time. What's the derivative of v with respect to time? It is the derivative of v is just 1, but then the chain rule says the derivative of v with respect to time is also dv dt. If we were taking the derivative of v with respect to itself, with respect to v, it would just be 1 dv dv, which just cancels out, so it's just 1. We kind of take that for granted most of the time in everything we've learned so far, but the chain rule applied rigorously and thoroughly means you have to do that. It's just that most of the time when we take derivatives, we don't have to do that, but we're taking the derivatives with respect to a different variable, so we do have to do it here. What's the derivative of this side with respect to time? Well, we take the 3 and we bring it out to the front. So the 3 comes here, right? And the 3 cancels out there. So it's 4 pi, and then we reduce the exponent by 1, so r squared. And then the chain rule says also that's times the derivative of r itself with respect to t. So dr dt. So the volume changes with respect to the radius, and the rate that the radius changes according to this equation. And you can also solve for dr dt and get how the radius changes in relationship to how the volume is changing. All right, notice this says that very often the key to relating the variables in a related rates problem is drawing a picture that shows the geometric relations between them. So let's look at example 1 here. All right, it says water runs into a conical tank at a rate of 9 feet cubed per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So we got a conical tank, all right? A conical tank that stands point down, and water is coming into this thing at a rate of 9 feet cubed per minute. All right, it says that the cone has a base radius of 5 feet. Okay. So you can imagine this maybe being at some industry where a process is happening here for manufacturing or something like that. And it says it has a height of 10 feet. So the full height is 10. All right. What else does it tell me? It says, how fast is the water level rising? So as water comes into this tank, I can think of at least 3 things that are changing, maybe more. There's probably more than that's changing. I'm sure there is. But at least these 3 things are changing. The volume of water in the tank is changing. The height of the water level is changing. And the radius, as the height increases, the radius is also increasing. We might also say the weight is changing and the mass, all these other things are changing too. But I think those are the 3 things that are going to be relevant to the problem: the volume, the radius, and the height. So let me get myself an equation that relates volume, height, and radius. Geometry is going to play a major role here. The volume of here's a little geometry lesson. The volume of any extended shape, we might call it a prism or something else. Any extended shape, whether it's a triangular prism, or a rectangular prism, okay, or a circular prism, which is not really a prism, it's a cylinder. But the volume of any of those things is given by the area. So the volume of a prism, we could say, or any extended face shape, is equal to the area of the face times the extension, or the distance it is extended. So like for a triangle, it would be 1/2 base times height times the length that it's extended. For a rectangular prism, it would be length times width times whatever depth it's extended. All right. What we're dealing with is a circle. So for a cylinder, let's imagine a cylinder like this. This is just an aside, by the way, to kind of help you with the geometry of problems like this. It's a free lesson. I won't charge you any extra. Would be the area of the circular face, which is pi r squared, times the distance that it is extended, which in this case we could call the height, or you might call it a length if it was on its side. All right. But notice what we have is not a full cylinder, but one that is coming down not at a parallel angle, but to a point in the center, at a conical cylinder. When that's the case, all you do when it's a cone like that, instead of a straight edge, you do 1/3 times that. And you might could see that. See, like this, you think of this as a third, this is a third, and this is a third of that volume. Okay, so what we have, let me write it a little neater. Our equation that relates these things is V for that cone is equal to 1/3 pi r squared h. Okay. Now, it says it wants to know when the height is 6 feet. So not when it's at the top, but when it's 6 feet deep. Okay, not when it's all the way to the top at 10, but when it's 6 feet deep. So another key to these problems is going to be somehow a lot of times you've got too many variables to deal with. Like we have 3 variables to deal with here. And what do I get information about? I have the height here, and I have the volume, the rate the volume is changing here, and I'm looking for the rate the height is changing, so I'm looking for dH dt, but I'm not given any information about the radius at this moment. So I want to try to eliminate that r variable by expressing it in terms of h. And here's how again, it's going to be, if you're strong in geometry, that's going to help a lot. Can we get the radius as just in terms of the height? And I think we can, using similar triangles. Okay, here's a triangle we have. So at the very top, it's 5, and the whole height right here would be 10. And then anywhere else, like here, we have a height of 6, and we have a radius that is associated with that we don't know, but we can solve for it based on this similar triangle situation. We can just use a ratio. 5 is to 10, just as r is to 6, right? 5 is to 10, the big ones, just as the little ones are to each other. So cross multiply and solve for r, and you get r equals 3. So in this moment, r equals 3. Okay. But I think I can also just replace the r in this volume equation with an h in general. Okay, and so instead of it at this very moment, let me just say any r to any h. Okay, so instead of just saying at the moment when the height is 6, I can relate the r to the h at any moment. At any moment when r and h are related to one another. I can say 5 is to 10, just as r is to h. So the radius at the top compared to the height at the top is going to be proportional to the radius at any height, the radius at any moment to that height at that moment. So from here, 5 is to 10 as r is to h. We cross multiply. 5h equals 10r. And I believe I want to replace this r. I'm going to replace that r with an h, something to do with h. So I'm going to solve for r. So r equals, I'm going to divide both sides by 10. 5/10 h, reduce the 5 over 10. R is equal to 1/2 h. Or h over 2, if you wanted to put h over 2, that's fine as well. So now this is equal to r, so that I can now replace that r with an expression with h. That eliminates one of my variables, which makes the problem a lot easier. And without doing that, it would be harder or even impossible. So these kinds of geometrical simplifications are going to be one of the keys to doing some of these problems. And it's just going to take some creativity, some imaginative thinking, some geometric acumen on your part to be able to do that. They're challenged in that way, but I think you can do it. So I'm going to replace the r with 1/2 h. So let me rewrite my equation. V equals 1/3 pi times 1/2 h squared times h. Now 1/2 h squared becomes 1/4 h squared, right? When we square the 1/2 and square the h. So 1/3 times pi times that, which then becomes v equals 1/12 pi h cubed. So I multiplied the 1/3 with the 1/4 and got a 12th, and I still have the pi, and the h squared times the h became h cubed. Now, all right, let me make myself some more room. Okay, for a mathematician, there's just never enough room, is there? 1/12 pi h cubed. V equals 1/12 pi h cubed. Now I'm going to take a derivative of both sides. Again, it's a rate of change, so it's with respect to the variable t. So the derivative of v is 1, and then dv dt, so it's just dv dt, equals the derivative of this. You bring your 3 down in front, so it becomes 3/12, but 3/12 reduced is 1/4 pi h squared, and then dh dt. All right, now I'm going to plug in stuff to this now. I'm looking for what? How fast is the water level rising? So I'm looking for this. I'm trying to find dH dt. That's what I'm trying to solve for. So I have to be able to then figure out what is dV dt and what is h, and hopefully that information is given in the problem. Do I know dV dt? All right, pause it and think about it. All right. Yes, I do know dV dt. What is dV dt? That's the rate at which the volume is changing in the tank. And the rate at which the volume is changing in the tank is 9 feet cubed per minute, because that's the rate at which the volume of water is entering the tank. All right, so that's 9. That is 9. Do I know h at this moment? Yes, it gives me that information. It wants to know how fast is the water level rising when the water is 6 feet deep. So at that moment, the h is 6. So just plug those numbers in. 9 equals 1/4 pi times 6 squared dH dt. And now I'm solving for dH dt. I'm getting dH dt by itself. So let's see, that's going to be 36. And 36 reduces with the 4 and becomes a 9. So I've got 9 equals 9 pi dH dt. My 2 9s cancel. So I've got 1 equals pi dH dt. Divide by both sides by pi. And dH dt is 1 over pi. If you want to get that as a decimal approximation, it would be around 0.32. And what would my units be? Feet per minute. That's the rate at which the height is changing. Height is changing at a rate of 0.32 feet per minute. When the volume is entering the tank at that rate, and when it's at that moment when the height is 6 feet. Now notice, as you get higher up the cone, it's going to take more water to make it go up higher. Like it's because like here, the water, like when you're down here, the water's going up really fast, right? Because there's not much to fill up. Because the radius is small, the height is going to change really fast. But as you get near the top, the height is going to go up a lot slower because it's going to take a lot more volume to fill up that extra area there. So we just found the rate at which that height is changing at that particular moment when the height is 6 feet. All right, that covers our first example. All right, here the book gives us just a nice explicit strategy, a summary strategy for approaching these problems. Now that we've done an example, you kind of see how we did this strategy. But first, it's a good idea to draw a picture and name the variables and constants in that picture that are given in the problem. Use t for time. Assume that all variables are differentiable functions of t. So related rates, it's always going to be taking derivatives with respect to t. Number 2, write down the numerical information in terms of the symbols you have chosen. So like if in our previous problem, v equals this, and dv dt equals that, and h equals this, and r equals that, and so on and so forth. 3, write down what you are asked to find, usually a rate. In our case, in the previous problem, it was dH dt. We were asked to find dH dt expressed as a derivative. dH dt. Number 4, write an equation that relates the variables. You may have to combine 2 or more equations to get a single equation that relates the variable whose rate you want to find. That relates the variable whose rate you want to the variables whose rates you know. So that's what we had to do. We had to write down our volume equation that related the radius and the height to the volume and all that. But then we also had to use another geometric equation to replace one of the variables to make my equation simpler, to make it be in terms of less variables. Because I don't know all the information of all the variables many times. Number 5, differentiate then with respect to t. So once you've got your equation and you've simplified it as much as possible, then take the derivative of both sides with respect to t. Then express the rate you want in terms of the rates and variables whose values you know. In other words, the other information given in the problem or that you've figured out somehow. Number 6, evaluate. Use known values to find the unknown rate. So that's just solving the equation, and then make sure your answer makes sense. All right, let's tackle example 2. All right, a hot air balloon rising straight up from a level field is tracked by a rangefinder 150 meters from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? All right, so let's use our strategy. Let's see what our strategy says to do first. It says to draw a picture, name the variables and constants. Okay? Let's draw a picture. So we have a balloon. It's a hot air balloon. I'm not going to try to be too good with my artistic skills here, but imagine that's a hot air balloon and it is rising. Okay. All right. And it is being tracked by a rangefinder 150 meters from the liftoff point. So here's this rangefinder. I don't know how to draw the rangefinder. Let's just draw it like that. That rangefinder is 150 meters from the liftoff point. I'm going to call that distance D. Is 150 meters. And I'm going to call this H. All right. And I believe I see a good shape to make, don't you? All right. At the moment, the rangefinder's elevation angle. So the elevation angle is the angle from the ground that the rangefinder is rotated above. So that is the angle theta right here. And you can obviously tell what shape we're going to be looking at now. A right triangle. But the moment that the elevation angle is pi over 4. So at this moment, that elevation angle is pi over 4. And it's increasing at a rate, so d theta dt, because it tells me that elevation angle is increasing at the rate of 0.14 radians per minute. So that's the rate of change for theta, d theta dt. It tells me that. So what do I want to use here? I think I'm going to use a trig equation. Something like this, theta, if this is theta and I'm doing these sides here, this looks like an opposite over adjacent tangent situation I can use. So I could say tan theta equals what? Equals h over d. Well, d here, so h is changing, so h needs to stay a variable. Theta is changing, so theta needs to stay a variable. But d itself is not changing. That rangefinder is still going to remain a distance of 150 meters from the liftoff point. That's not changing at all. So D doesn't have to be a variable. D can just be a constant. It's just 150. Let me see if I have obeyed my instructions here. Write down numerical information. I think I have done that. Write down what you're asked to find. I haven't done that yet. What are we asked to find? How fast is the balloon rising? How fast is the balloon rising? What does that mean I'm finding? What rate is that? That is dH dt. That's what I'm trying to find. All right, what's my next step say? Write an equation that relates to variables. I've already done that. Differentiate with respect to t. So I have written down my variables here. I've written down my equation. Is there any other simplifications I need to make to that equation? Like, can I write h in terms of theta? Or I think I've already. I don't think I can do anything else to that. So let me go with it and see what happens. I'm going to. I will rewrite it like this because it makes the derivative a little bit more obvious on the right side. All right, so the derivative of tan theta, with respect to time is going to be, the derivative of tangent theta in general is secant squared theta. And then the chain rule says then take the derivative of the inner piece, which is theta itself, with respect to the variable of differentiation, which is t. So d theta dt. Secant squared theta times d theta dt. That's the full derivative of the left side. And the derivative of the right side with respect to t, the derivative of that in general is just going to be 1/150th. But then it's times, the chain rule says to then take the derivative of that inner piece, which is just h with respect to t. So dh dt. Now, I am looking for dh dt. The question is, do I know theta? Do I know d theta dt? I actually do know theta. Theta is pi over 4. And I do know d theta dt is 0.14. I think I'm done. I mean, it's just all over but the crying now. So it's going to be secant squared of pi over 4 times 0.14 equals 1/150th dh dt. All right, so secant squared of pi over 4, let me think about that. Secant is the reciprocal of what? It's the reciprocal of cosine. So that's the same thing as saying, what is cosine of pi over 4? Cosine of pi over 4 is, that's the same thing as cosine of 45 degrees, which is √2/2. So then what we have is we have secant of that would be the reciprocal of it, would be 2/√2. Secant of pi over 4 is 2/√2. So I've got, let me rationalize my denominator here. Times √2 times √2. That's going to be what? That's going to be 2 on the bottom and 2√2 on top. So the 2's cancel. So it's just √2. So secant of pi over 4 is just the square root of 2. So I've got the square root of 2, but it's secant squared. So that's squared times 0.14 all right, equals 1/150th dh dt. All right, here goes just doing some arithmetic now. So that's the square root of 2 squared is just 2. So 2 times 0.14 is 0.28. Now I'll get rid of that 1/150th by multiplying by 150 on both sides. And I get, when I multiply that, I get 42 equals dh dt. And I've solved it. At the moment that in question here in the problem, at that very moment, the balloon is rising at a rate of 42. What would be the units here? Meters, right? Meters, because it's given meters, and minutes. So meters per minute. All right, example 3. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. So a police cruiser is coming from the north, and the car that is chasing is moving east. All right, so if I'm drawing a picture, the one car, I'm just going to draw it as a little rectangle here, okay, is approaching from the north, so it's going south because it's coming from the north. The other car is moving to the east. So it's coming from the north and it's approaching this intersection where the other car has already turned the corner and is going east. When the cruiser is 0.6 miles north, okay, 0.6 miles north of the intersection, and the car is 0.8 miles to the east. Let me draw that. Let me redraw that a little bit farther away. The police determine with radar that the distance between them and the car is increasing at 20 miles per hour. So the distance between them and the car, we'll call this D, is increasing at 20 miles per hour. Let me do some different variables here. I don't know. I think I'm going to need maybe some more letters, and so it's kind of like all these are distances. So I don't want to call all of them D. Let's say this is A, this is B, and this is C. How about that? That'll work. You could call it X, Y, Z. It doesn't matter what you call it, but you could call it D1, D2, D3 if you want. All right. So what did it just give me? It says the distance between them is increasing at 20 miles per hour. So that's DC dt. That's what it just gave me. DC dt is 20. If the cruiser is moving at 60 miles per hour, what did that just give me? dA dt is 60. I think actually it's negative 60. Negative 60 because A is shrinking, right? The cruiser is moving 6 miles per hour, so A is actually getting smaller. So the rate at which A is changing is negative 60 miles per hour. At the instant of measurement, what is the speed of the car? So what am I looking for? I'm looking for dB dt. That's what I'm looking for. All right. So I feel like we're going to be using, why don't you guess what we're going to use? I'm thinking we're going to use the Pythagorean Theorem. Aren't you thinking that? That's what I'm thinking. So that's pretty simple. A squared plus B squared equals C squared. And I think I've got all the information I need. I don't think I have to simplify anymore. I can just take derivatives with respect to time. So 2a dA dt plus 2b dB dt equals 2c dC dt. Now, do I have all the information I need? Do I have the information, the A and the dA dt and all that? I think we do. Let's try. What is A? I think A is given. It is 0.6 at that moment. And dA dt, we've already established, is negative 60 at that moment. And B at that moment is 0.8. And dB dt is what I'm trying to find, so that stays a variable. and C at that moment. All right, C is actually something I don't know, but I can figure that out, can I? I can use the actual Pythagorean theorem with the numbers to figure out C. So 0.6 squared plus 0.8 squared equals C squared, or I can just say C is the square root of those. So let me do my calculator here. So I did it in my calculator and I found C to be 1. So C is 1. We could write the 1 or just not write it. dc dt. Well, I know dc dt. It was given already. dc dt is 20. All right. Now, let's just do some arithmetic. All right. 2 times negative 60 times 0.6. That's negative 72 plus 2 times 0.8, 1.6 dB dt. Equals 40. Add 72 to both sides. That's 110, 112. Divide by 1.6. And I get 70. So it looks like that car's speed at that moment is 70 miles per hour. All right, next example. I'm skipping example 4 from the book just because I thought it was a little bit more complicated than it needed to be. So we're going to go to example 5. A jet airliner is flying at a constant altitude of 12,000 feet above sea level as it approaches a Pacific island. The aircraft comes within the direct line of sight of a radar station located on the island, and the radar indicates the initial angle between sea level and its line of sight to the aircraft is 30 degrees. How fast in miles per hour is the aircraft approaching the island when first detected by the radar instrument if it is turning upward at the rate of 2/3 degrees per second in order to keep the aircraft within its direct line of sight? So if I'm drawing a picture of that, we've got this airplane. I'm just going to draw the airplane as a triangle, I think. We got this airplane, and I've got a radar down here. And the radar detects this airplane at the moment that the airliner is 12,000 feet above sea level. All right, so I think I'm going to draw the triangle this way. Let's see. No, I think I'm going to draw it this way. Okay. And so that, let's call that H, and that is 12,000 feet. And we have this angle theta, and it tells us that d theta dt is 2/3 degrees per second. All right. And that theta at that moment, theta is 30 degrees. Anything else? I don't think there's anything else. I'm looking for how fast the plane is traveling. So that would actually, like, what's the plane traveling corresponds to this, right? Because that's what's shrinking as the plane is traveling horizontally. So I'm looking for the rate at which that is decreasing. Let me call this, I'll call it X. Sure. Go ahead and say theta is 30 degrees. And I can go ahead and know X, can't I? I can say tan of 30 equals 12,000 over X. And solve that in the calculator. X equals 12,000 over tan 30, which equals 12,000 divided by tangent of 30 equals 20,784. 20,784.6. Okay. And I'm trying to find dx dt. That's what I'm trying to find. All right. I think I want to set this up with, again, the tangent equation. Tan, I'm going to see if this works. I hope it will. Tan theta equals h over x. H, though, doesn't have to be written as h because it's not changing. It's not a changing quantity. It's a constant, 12,000. It's not changing its height. It's remaining at an altitude of 12,000 feet. So I'm just going to put that as the constant 12,000. And so now I'm going to rewrite this. I think I'm going to go ahead and do the derivative, but before I do that, I'm going to rewrite it as tan theta equals 12,000 x to the negative 1 to make the derivative simple. So let's go ahead and do the derivative of both sides with respect to t. All right, the derivative of tangent is secant squared theta. And then chain rule says d theta dt equals, bring the negative 1 in front, it becomes negative 12,000 x to the negative 2. But if you don't mind, I'm just going to write, instead of x to the negative 2 right there, I'm just going to say divided by x squared dx dt. Okay, let's go ahead and insert what we know now, all the numbers that we know. We know that theta is 30 degrees. If I do cosine of 30, cosine of 30 is root 3 over 2. Then I'm going to square that. So root 3 over 2 squared is it's going to be 3 over 4. So secant is a reciprocal of that, so it's going to be 4/3. 4/3. I already squared it, so it's the secant squared of theta is 4/3. Now d theta dt, let's think about that. 2/3 of a degree per second. I can't multiply by degrees. If multiplying by degrees is going to change all the units. It's going to mess up the units. I'm going to change the units to radians because radians is a unitless unit. Now, if you don't remember that from trig, you can take my word for it for now. I can explain that to you later. It's a lesson for another time. But just take my word for it that radians are actually unitless. So I'm going to change it to radians. 2/3 degrees per second. And I'm going to go ahead and change it to radians per hour because it wants the answer in miles per hour. So instead of degrees per second, I'm going to radians per hour. So 180 degrees is pi radians. Cancels the degrees. All right, 60 seconds is 1 minute. That cancels the seconds. And 60 minutes is 1 hour. Cancels the minute. So now that leaves me with radians per hour. All right, do that calculation. 2/3 times 60 times 60 divided by 180 equals. I get 13 1/3. So 13 1/3 is the same thing as 40 thirds. 40 thirds pi degree, not degrees, radians per hour. You're going to have to do that for the units to work out here, or it'll be the wrong answer. So 40. Come on now, what's going on? 40 thirds pi equals negative 12,000 over, what was that value of x? It was 20,784. 2784.6. And that's squared dx dt. All right, now I got to do a lot of arithmetic. That's going to be 160 pi over 9. I'm going to go ahead and multiply by the reciprocal on both sides. 20,784.6 squared over negative 12,000. Negative 12,000. 20,784.6 squared dx dt. So I'm multiplying by the reciprocal of this on both sides to get rid of that. It's because I'm trying to solve for dx dt. I'm trying to get that by itself. So that cancels that, and dx dt equals, I got to do some calculator magic here. 20,784.6 squared divided by negative 12,000 times 160 times pi divided by 9 equals negative 2,10,617.4, and that's feet per hour. So now I need to change that to miles per hour. So let's change that to miles per hour. There's 5,280 feet in 1 mile. So just divide by 5,280. And I get negative 380.8 miles per hour. That's my answer. Now, does that make sense? It makes sense that a plane would be going 380 something miles per hour, and it makes sense that I got a negative number also because that's the rate of change of that length right there, that distance, and that distance is decreasing. It's decreasing at a rate of 380 miles per hour. So I'm liking that answer. So that should be it. And that's kind of all the examples that I need to do, I think, with you. That's all the examples in the book. So hopefully that gives you a good idea. I know this is pretty tough stuff, pretty complicated. It's a good challenge for you, though. It's a really good challenge for you to try to work through math, see how this stuff applies, using all your geometry and trig and algebra and arithmetic and all those skills that you've built up over the years, using all those skills to figure out these problems, applying calculus to it, interpreting the words and putting the values in the words, in the word problems in the right spots and all that good stuff. You're going to struggle on some of these problems on the homework, and that's okay. When we just try to get them all done as best you can. Maybe you can get, if you can get 7 out of the 10 done, good. And if you can't do the other 3, we're going to look at some of those in class. So you can ask me about some of them in class. Good luck with it. See you next time.